Hello everyone. Today we will give the final presentation on our group project, Real-Time Information Sharing Between Connected Vehicles. So this presentation is given by me, Huyan, and also my teammate Henry. So first of all, Henry is gonna give the whole introduction, where the problem came from, what are the technologies we used, and then I'm gonna introduce what we learned from our research and what we developed from that.
When vehicles need to get information about the environment, most of the time they rely on their own camera, radar, and the driver's eyes and ears. We want to know if there is a way traffic information can be shared more efficiently than this method. For this purpose, we want to build a system where vehicles, pedestrians, and road infrastructures are connected together to share the information over a network. In such a network, every vehicle, pedestrian, or road infrastructure can be considered as a node and communicate with other nodes. In the launch stage of the project, the title we set for our project was Real-Time Traffic Information Sharing Between Autonomous Vehicles. However, during the continuous research, we realized that in our problem definition, automated driving was not responsible for information sharing. Instead, connected vehicles are more precise to the problem. So we modified the project title to Real-Time Traffic Information Sharing Between Connected Vehicles. Information would be shared when road components are connected in the network. A network of connected vehicles does not only include vehicle-to-vehicle communication. It could also include vehicle-to-pedestrian communication and vehicle-to-infrastructure communication. In our midterm presentation, we received comments asking what is considered as road infrastructure. The infrastructure includes traffic signals, crosswalks, and traffic signs such as a stop sign. Altogether, when these parts are connected together in a network, it becomes vehicle-to-everything network. Our original idea considered only vehicle-to-vehicle communication, but compared to the latter version of vehicle-to-everything, vehicle-to-everything provides much more potential and probabilities for real-life applications of connected systems. Speaking of applications, a vehicle-to-everything network could help drivers and overall performance of the traffic. For example, there could be a warning of potential collisions to avoid traffic accidents. Traffic information sharing and communicating would bring tighter vehicle following control, which allows vehicles to keep a shorter distance from each other. Vehicle-to-everything allows information to be shared between vehicles and pedestrians, so it could enhance the road safety. Now that we know connected vehicle systems can help us enhance the efficiency and the safety of road transportation, let's take a look at what technologies we could use to support connected systems. We will first introduce dedicated short-range communications, or in short, DSRC. Then we will discuss a newer technology of cellular-based communication. Although there are also other potential solutions like Wi-Fi, satellite, or Bluetooth, these solutions in general did not attract too much attention from industries and did not have relevant standards in application. First, we want to introduce dedicated short-range communications, or DSRC. It follows a Wi-Fi-like standard, and it is designed specifically for road transportation. DSCR supports 10 to 20 times communication per second for all participants in the network. One feature of DSRC is its low latency that fits the situation of time-critical and safety-critical message communication. The downside is DSRC was primarily designed for short-range communication and it is not adequate for long-distance communication. In addition, DSRC is a relatively old standard and did not enjoy the advancement of new technologies, especially commercial cellular technology development. We will then introduce the new cellular-based solution in the next slide. The new cellular-based communication is very similar to our cell phone's network. It connects every node through cellular signals. With the development of new 4G technologies, we are going to talk about the advantages of implementing vehicle-to-everything services in the new cellular-based communication. Any existing base stations or infrastructures can be easily reused for vehicle-to-everything services. Service providers do not deploy new facilities to support this function. Vehicles are easily connected to current networks, such as the Internet. New LTE-based services would support a bigger range of coverage and high bandwidth, which solves the old questions of DSRCs. However, a cellular network may have a relatively high delay, which may cause potential problems about some critical conditions.
So in the previous slides, my teammate introduced DSRC and cellular network to you, and also their benefits and downsides. And now let's do a comparison of these two. First, DSRC is supported by the US Department of Transportation and some vehicle companies. The study started around 2004. So now it is a pretty well developed technology now. On the other hand, cellular network is supported and developed by some cell phone service providers. One of the underlying technologies of cellular network is called LTE V2X, sometimes referred to as LTE or LTE-V. The study for that started around 2017, which means it is still a new technology under development. It is not as complete as DSRC. One of the major differences between DSRC and LTE is that DSRC has so far the least latency, whereas LTE has higher latency, which makes it not as reliable as DSRC for time critical or safety critical messages. However, LTE does have some other advantages. For example, it has larger bandwidth. So compared to DSRC, LTE can support other applications like file download. For this reason, some research papers have proposed that LTE will be suitable for entertainment services. Another limitation of DSRC is that it only covers a very short range. Normally, the area covered is like around 1 kilometer. Compared to that, cellular network, their base stations cover a much wider area. We also mentioned before that V2X provides a really wide range of applications. So we believe that it is unlikely that a single technology, either DSRC or LTE, is able to support all these varieties. So based on their differences, each individual pros and cons, we consider combining these two together to support the different applications by V2X. Now that we decide to combine these two together, the first question will be when to use DSRC and when to use cellular network. Well, the basic idea here is that we apply DSRC for V2V applications and apply cellular network, especially LTE, for other aspects like V2I, I2V, and V2P. Because information being exchanged between vehicles is mostly real-time traffic condition. For example, it could be some vehicle sending message to vehicles around it when this vehicle has a sudden breakdown. Here, the message must be sent very fast so that the other cars around it can take actions as early as possible to avoid collision. We can see from this example that V2V messages is really time critical. Therefore, we apply DSRC, which is this low latency technology. We choose LTE for V2I, V2P, and I2V because first, it has larger bandwidth, and second, it covers wider areas. As proposed by previous research papers, LTE is suitable for entertainment. In other words, not for transporting time-critical messages between vehicles. So it could be used, for example, to talk to road infrastructures to get road condition. For example, a vehicle could talk to other road infrastructures to get the road condition from its destination, so it could make better route planning before departure. This message is not time urgent, but the destination could be far away, so it might be inefficient to use the SRC here. Notice that it is possible to use the SRC here if you don't mind the message takes several hops before you get to the destination, but that would be time consuming and it's also it's also wasting the DSRC's bandwidth. We could totally use LTE instead and save that DSRC's bandwidth for other time or safety critical messages. So that's our basic idea, but we could also use some backup plans here. There is a scenario mentioned in a previous paper where two vehicles are going in opposite directions and both of them are moving with really high speed. Imagine it's a freeway. So the relative speed is so high that it might even weaken the DSRC signal. In this case, where DSRC is not as efficient as expected, we could use LTE instead. If the weakened signal of DSRC is detected, then we could switch to the data transmission like from V2V to V2I and I2V because cellular network is not affected in this case as much as DSRC. So we convinced ourselves that a combination of DSRC and cellular network is more viable. Now that we plan to apply them for different applications, I would also like to talk about their interworking. So first of all, cellular network can serve as an access to the internet. So the vehicle and the driver won't be restricted to only the V2X system. Remember when we compared DSRC and cellular, we said LTE is more suitable for entertainment, right? In fact, with cellular network involved, you can get access to whatever you can get from your phone because the base stations of your phone service providers can also provide a base for your vehicle. Also, in the previous slides, we talked about a special case where DSRC is not working as expected. In cases like that, cellular network is working as a backup. That leads us to a technique called handover strategy. This happens when a moving node, usually a vehicle, when it leaves the range of one previous network and enters another one. For example, when a vehicle is too far from other nodes, so it's not performing DSRC, or it is no longer covered by a cellular base station, this is when the handover strategy is put into use. So there are two types of handover strategies. The first one is called horizontal handover. It happens when your data transmission session is transferred from one point of access to another one, and the transfer is to a network using the same access technology, which means you're transferring from a DSRC network to a DSRC network, or you're transferring from one cellular base station to another cellular base station. The second one is called vertical handover, and this is the one we're more interested in. This happens when your transmission session is transferred to a different network, which means it is transferring between DSRC and cellular. A proper handover strategy is definitely critical for data transmission because your transmission session, it is very likely that this session is still ongoing, active, when your vehicle leaves the range of the previous network. The handover strategy is mostly handled in network layer 3. There are solutions posted for it. For example, the Internet Engineering Task Force, they developed IPv6, which is a network layer protocol. It allows you to resume and restart your internet activities when you are transferring between different networks. The handover strategy can also be handled in link layer 2, but we are not studying that because that layer is too low, too fundamental. And finally, the potential problems. Of course, we hope our design is perfect, but unfortunately, it's not. The current study for the combination of DSRC and cellular is based on what these two technology already look like right now. But technology is developing. DSRC and cellular are both emerging over time, so that should be taken into account. Also, the future trend of technology is that cellular base stations will cover smaller areas for better internet practice. So we might need to make alternative plans when we are using cellular network as a backup for DSRC, because we need to think more before we choose to switch from DSRC to cellular network. And thank you for listening. That is our final presentation for this project.